Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 26, 2026, just 3 days ago. It uncovers why diffusion language models often fail to achieve true parallel generation, and introduces a solution called NAP that improves accuracy on the GSM 8K benchmark from roughly 47% to 61%. The paper is titled, Why Diffusion Language Models Struggle with Truly Parallel Non-Autoregressive Decoding. And as we'll see later, the implications for model training are quite significant. And for those interested in the implementation, the authors have shared their code on GitHub. So, Figure 1 visualizes this decoding behavior explicitly. In the first two panels, labeled A and B, we see standard diffusion models like LLADA8B and Dream7B. Despite having the freedom to decode in any order, the points form a strict diagonal line, showing they effectively collapse into a standard left-to-right generation process. Compare that to the author's method, NAP, in panel D on the far right. Here the pattern shifts to distinct parallel bands, which indicates the model is successfully generating multiple sections of the reasoning chain simultaneously. Well, Figure 1 just showed that models naturally drift towards sequential behavior, so Figure 2 asks a crucial follow-up. What happens if we force them to be truly parallel? Here, we track accuracy on GSM 8K and Math 500 across 3 decoding strategies. The results are stark. If you look at the RAND group on the right of the first chart, performance collapses when sequential dependence is broken. For instance, the blue bar for Dream7B plummets from about 78% in the standard setup down to just 34% here, proving that these models currently rely on sequential order to reason effectively. Alright, since the previous figure showed that performance collapses without order, Figure 3 investigates the source of this dependency. It plots sequential dependence, or seq-dep, against sequence length for 2 standard datasets, Open R1 Math on the left and FineWeb on the right. In both cases, the green trend line rises steeply and stays high as the text gets longer. This indicates that standard training data is intrinsically sequential, which conditions the models to treat reasoning as a linear chain rather than a parallel process. Okay, while the previous figure analyzed the data itself, Figure 4 reveals how this affects the model during fine-tuning. The chart tracks global ARness scores over 10,000 training steps. Look at the solid blue line for LLADA8B. It climbs steadily by 0.08, showing that standard supervision forces the model toward strict left-to-right generation. In contrast, the dashed green line at the bottom shows the NAP method, which actually lowers the score, successfully preserving the model's ability to decode in parallel. So, having visualized the training trend in the previous figure, Table 1 now quantifies this autoregressive bias during inference. It compares strict AR order against arbitrary order, or AO, where the model picks tokens based on confidence. Under the AO columns on the right, notice that Dream7B has an ARness score of 0.92. This implies the model defaults to a nearly sequential path, even when free to decode in parallel. Furthermore, adding the fast DLLM accelerator pushes these scores even higher, for instance boosting LLADA8B from 0.73 to 0.87. Well, Figure 6 illustrates the core solution, the parallel forced decoding framework. Instead of a single text stream, the model uses a structured canvas with multiple independent sections, labeled here as Think 1, Think 2, and Think 3. Notice in Step 1 and Step 2 that the model fills these blocks simultaneously, exploring different reasoning paths, like finding roots or factors at the same time. Finally, the summary block on the right aggregates these parallel thoughts into a single coherent answer, effectively forcing the model to break its sequential habit. Alright, following that visual breakdown, Table 3 presents the quantitative proof across GSM 8K, Math 500, and GPQA. The crucial test lies in the low-step regime, specifically the row for 256 steps, where the model must decode 4 tokens at once. Look at the Dream7B results on the right. The standard long chain of thought baseline struggles here, dropping to 46.5% accuracy. In contrast, the NAP model in the blue column jumps to 60.9%, a massive 14.4% improvement. This confirms that while standard models falter when forced to be parallel, NAP successfully decouples reasoning quality from sequential order. Wrapping up, the big takeaway here is that a parallel architecture does not guarantee parallel speed if the training data remains linear. The paper proves that standard sequential reasoning forces models to ignore their parallel capabilities. By restructuring this data, the NAP framework effectively decouples reasoning from order, unlocking the true potential of non-autoregressive generation. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.